Welcome viewers to the second lecture for the online series of lectures for the course of Algebraic Topology 2. In the previous lectures, we discussed homology groups of simplicial complexes in various dimensions, except for the zeroth dimension. We never talked about the zeroth homology group of a given simplicial complex. So in this lecture, we are going to first address this notion of zeroth homology group of a given simplicial complex. Then we'll define cone, the concept of cone related to a given simplicial complex, and how it is useful to determine the homology groups of an n simplex. Okay, and then we'll talk about the notion of reduced homology groups of a given simplicial complex. So let's get started with the with the definition of certain useful terms called star of a given face of a simplicial complex. So we start with this definition of star of a vertex of a given simplicial complex. If V is a vertex of a simplicial complex K, then the star of V, denoted by St of V, is the union of the interiors of all those simplices of K that have V as a vertex. Okay, so let me give you an example of a simplicial complex. Let me draw the diagram here. Let me draw it on the far left so that I can always keep it. Okay, so I am drawing a two-dimensional simplicial complex. Okay, so these are the one simplices that I'm drawing now. These are all the one simplices. Okay, so so these are the two simplices. Okay, so if you want to uh, denote those two simplices by shaded regions, then you can do it like this. Okay, so in other words, these are all two simplices. So these are two simplices. So this is another subcomplex two-dimensional. Well, if you want to, you can put a so two simplices here. Okay, good. Now, so let us denote this vertex of this complex K by V0. This vertex at the right hand corner, upper right corner, as V1, and this vertex here as V2. Okay. So now, regarding this complex K, there are okay. So I think at this moment, let me okay. So so there are three one simplices and two simplices that contain the vertex v1 of K. Let me show that in the diagram. This is the vertex v1. Okay, and this is this edge contains v1. This edge also contains v1, and this edge also contains v1. Okay, so there are three one simplices altogether which contain this common vertex v1. Okay, and this is a two simplex. This is also a two simplex. They both contain v1. Okay, so there are two simplices that contain this vertex v1. Okay, okay. uh, so also, now, about okay, so this was the story of the vertex v1. Now, the closure of star of v. Okay, star of v is an open set. The closure of this guy is called the closed star of the vertex v, and is denoted by this closed set is denoted by overline star of v. Okay, and then you take uh, the difference between these two sets. The set closed star of v set minus the star of v is called the link of v, and is denoted by LKV. Okay, so these are the three notions: the star of v, the closed star of v, and the link of v, that are important for the future results in this lecture. So in this diagram, we see that the interiors of the of these five simplices, right? So there are these three one simplices, and there are these two simplices. So if I just take the interior of these five simplices, so this is the interior of the edge, this edge containing v1, and this is the interior of the top edge containing v1, and the right edge containing v1 has the interior given by this open set. Okay, so you take the union of these guys, along with the union of the interior of these two simplices, what you get is this open set here, okay, which is bounded by this rectangle, the boundary of which is the whole rectangle. So this is what I'm going to write here. The interiors of all these simplices is called ST of V1, star of V1. Okay, and according to the definition of the link of the vertex V1, we know that LKV1 is going to be equal to the closed star of V1 set minus ST of V1. Which is this L-shaped boundary, okay, this guy. If I subtract the subtract the set ST of V1, right, which is the union of these five, the interiors of these five simplices from the closed star of V1, which is the whole region. Okay, remember that these two edges fall into the interiors. Okay, here, so that what we have is we are left with this L-shaped region, L-shaped shaped, line, which is the link of V1. Okay, good. Similarly, you see that if you consider this vertex V2, then V2 is contained in this this edge, also this edge, this edge, this edge, and this edge. Okay, so there are five one simplices that contain V2. Okay, and how many two simplices contain V2? This two simplex contains V2. This two simplex contains V2. Similarly, this two simplex also contains V2. Okay. So now if I try to form the link of V2, okay, then we'll see that it's going to be this line and these two lines. So this guy and this inverted L-shaped line together forms link of V2. Okay, good. Now about the vertex V0, you see that there are 1, 2, 3, 4, 5 two simplices that share this vertex V0, and there are 1, 2, 3, 4, 5, 6 one simplices that contain the vertex V0. Okay, so now if I try to form the link of V0, that is going to be this one-dimensional complex given by the union of these lines, line segments. Okay, so this pentagon, no, this is a hexagon. 1, 2, 3, 4, 5, 6. This hexagon, the boundary of this hexagon, of course, is link of V0. Okay, good. so now we are all good to state the first theorem of our lecture. So let me state it without erasing the diagram. Okay, so let me first state it. Theorem 1, which states that if we have a complex denoted by K, let K be a complex, then the group H0 of K, okay, which is the zeroth homology group of the given complex K, is free abelian. It doesn't have a torsion part. Okay, if this collection is a collection of vertices, is a collection consisting of one vertex from each component of K, component of mod K, of course, which is the underlying space of the given complex K. Okay, so mod K is a topological space, and it may be a disconnected space. So it has various components. So we pick up a vertex from each component of mod K. All right. Then the homology classes, of mod K. So by then the homology classes of the chains V alpha form a basis for H0 of K. So what I mean by homology classes of chains is the following. It means that we take all the zero chains that are cycles but not zero boundaries. So let me write it. It's the set of all zero cycles. In other words, the zero chains which are cycles. In other words, they are zero cycles that are not zero boundaries. Okay, these are called homology classes of the chains. Okay. And we'll see later that how reduced homology appears in this context. Okay, so for the moment, just think about it as zero cycles that are not zero boundaries. Okay, all right, so let us move into the proof. So the proof is divided into two steps, I believe. Yes, so let me go over the steps of the proof. So step 1, if V W are two vertices of the complex K, are two vertices of K, then define an equivalence relation. First of all, define a relation. You need to check later that it's an equivalence relation. Then define a relation V is equivalent to W if there is a sequence of vertices A0 all the way up to AN, such that A0 is the vertex V and AN is the vertex W, and AI plus 1 is a 1 simplex of K. Here I runs from 0, 1, 2 all the way up to n minus 1. Okay, so if I take I to be 0 here, I get A0, A1, and A0, A1 is supposed to be a 1 simplex of K. Similarly, you choose all the other values of I, and you must have AI plus 1 to be a 1 simplex of K. All right, so for example, you choose I to be n minus 1, and you want an minus 1 an to be a 1 simplex of K. Okay, so it means that, well, so in this example, say you have in this picture K, in this complex K, you use V0 and say this is V2, so we can say that V0 is equivalent to the vertex V2 because V0 and V2 can be connected by one simplices lying on the complex K. Say we can go to V2 from V0 via this path where all of these line segments lie in the complex K. Okay. Similarly, you can go from V2 to V1 this way. So V2 is also equivalent to, so V2 is also related to V1. Okay. And it is an easy exercise for one to check that this relation is indeed an equivalence relation. Okay. I leave it as a small exercise for you. Okay. So check that this relation is an equivalence relation. And intuitively it's clear from the previous diagram of the complex K. Okay, so I need some room. Now, given vertex V of the complex K, define the set C sub V to be the union of these open sets. Star of W, where W is equivalent to this given vertex V. So you take all those vertices that are equivalent to, that are related to this vertex V, according to the equivalence relation that we defined earlier a while ago. So, and you collect all those stars corresponding to those vertices which are equivalent to each other, and take the union of all those stars, and that gives you this set C sub V. This is our equation number 1. The first goal is to show that each such CV is a component of the topological space mod K. Okay, this is the first goal. So you pick up, so in the diagram, in this diagram which we call figure 1, which is complex K, you see that there is one such component in for the complex K. Since complex K is connected, it's not a disconnected complex, so we have one such C of V. It's the whole complex. It's the whole complex itself, C of V in this example. Okay. First of all, try to note that CV defined by equation 1 is an open set because it's the union of open sets, and we know that the union of any collection of open sets is open from our knowledge of topology, point set topology, right? Now we show that CV defined by equation number 1 is path connected. Okay, let X be a point in CV. We need to show that there is a path from the point V to the point X lying entirely in the set CV. Now, since X lies in CV, according to the definition of CV, there exists a vertex W which is equivalent to the vertex V such that X belongs to star of W. Okay, follows from the definition of CV. Now, since W is equivalent to V, there is a sequence A0, A1 all the way up to AN of vertices of the complex K such that the initial point of this sequence A0 is V and the final vertex of the sequence AN is W, and each line segment AI plus 1 for I from 0 to all the way up to n minus 1 lies in the set CV. Okay, that was the definition of the equivalence relation, right? Now, X is in star of AN by hypothesis, right? Where AN is equal to W. Where is that? X is in star of AN by hypothesis. Since star of AN is star shaped, star shaped with respect to this point AN, which is W, the line segment WX lies in star of AN, right? Which is contained in CV. In other words, All right. Um, since star of an lies in CV, um, and wx, the line segment wx lies in CV, we conclude that the path a0, a1, a and x. Okay, so the path joining all these points lies entirely in C sub v. Okay, in other words, there is a path joining this point a0, which is just the vertex v, and this point x, and x lying entirely in the set CV, right? This is what we wanted to show. It proves that CV is, it proves that C sub V is path connected. Right? So I don't need this diagram anymore. Let me erase everything. So now we show that distinct sets C sub V and C sub V prime, we want them to be distinct so that V is not equal to V prime. Okay, so V is not equal to V prime. And we show that such two distinct sets are disjoint. Okay, so suppose the contrary. So we proceed by contradiction. Suppose the contrary holds, or suppose the contrary with x belonging to the intersection of these two sets. Then and since x belongs to both of these sets, both of these open sets, and from the definition of C sub v and C sub v prime, there exists W with W being equivalent to a V. So so now just consider X being in this C sub V, in the set C sub V. So it means that from the definition of C sub V, there exists a point W with W being equivalent to V, such that X belongs to star of W, this guy. Okay, and when we consider X belonging to this set C sub V prime, we know that there exists a point W prime with W prime being equivalent to V prime, such that the same X, this guy, belongs to star of W prime. Okay, so it entirely follows from the definition of this open set C sub V, which is the union of all stars of the vertices that are equivalent to each other. Okay, now let us get back to the concept of barycentric coordinates that we discussed in the towards the end of the of the course of algebraic topology 1. Okay, so if you don't remember them, refer back to the lectures there. Probably in the 7th lecture or in the 6th lecture we discussed this concept of barycentric coordinates. Okay, now the barycentric coordinate t sub w of x. Remember that you can find the barycentric coordinate of a point in a simplex relative to some other point. Okay, and it means that we are referring to the barycentric coordinate of this point x relative to this vertex, relative to this point w. Okay, so with respect to w is positive. Okay, since x belongs to star of w. Okay, so check for the detail of these things, check the discussions following the definition of barycentric coordinates on page 20 to 21 in Muncres. In the book by Muncres, which we are using as the reference text. Okay, so we know that this, as long as x belongs to this star of w, this guy is positive, right? This barycentric coordinate. Similarly, we know that the barycentric coordinate of x with reference to the point w prime is also positive. Okay, so barycentric coordinate, so you can find the detail there that I mentioned here, but in any case, let me mention it here. Barycentric coordinate of a point, it can be 0. That's the thing. Of a point with respect to vertex v can be 0. Okay, if the simplex having the point in its interior does not have v as a vertex. Okay, so suppose you have a complex like this, something like this. Okay, and you're referring to this point x, and so x is in the x lies in the interior of this simplex, right? And if your v is not a vertex of that simplex that contains x, right, then the barycentric coordinate of x with respect to this vertex is going to be 0. So that's what I have written down here. if it does not have V as a vertex, then the barycentric coordinate of this guy lying in the interior of that simplex, which does not contain V as a vertex, is going to be 0. Otherwise, it's strictly positive. Otherwise, it's strictly positive. You'll see that when you go over this discussions, you'll see it there. Okay, good. And it's immediate that, from the definition of a complex, that the point x is interior to precisely one simplex of k. Okay, so so if say for this diagram, for this complex k, x is in the interior of this bold 2 simplex, right? There is no other simplex of the complex k that contains this point x. Okay, good. The point x is interior to precisely one simplex of k. Since both tw of x are strictly positive, tw of x and tw prime of x are both positive. Okay, and since they are both positive, w and w prime must be vertices of the simplex, of the same simplex. That's the point, of the same simplex that has x, because this is the unique simplex that contains the point x, that has x in its interior. Okay, it means that w prime must be a one simplex, right? Since w and w prime are both vertices of the same simplex, it means that w prime must be a one simplex of k, so that w is equivalent to w prime, according to the definition of the equivalence relation that we defined in the beginning of the lecture. Okay, so we have w being equivalent to v and w prime being equivalent to v prime, right? Because this is from a hypothesis. We have chosen w to be equivalent to v, and we have chosen w prime to be equivalent to v prime, and we have just seen that w is equivalent to w prime, and since twiddle is an equivalence relation, is an equivalence relation, we must have V to be equivalent to V prime, right? So from the definition of the open set C sub V, if V is equivalent to V prime, it forces us to believe that C sub V is equal to C sub V prime, which contradicts the fact that C sub V and C sub V prime are distinct. This is a contradiction. C sub V and C sub V prime are supposed to be distinct. Okay, good. So which means that our primary assumption was incorrect. C sub V and C sub V prime are disjoint. Okay, so being connected, open, and disjoint, the sets CV are necessarily the components of this topological space mod K. Okay, they are distinct, they are connected. They are connected, open, and disjoint, and hence they are components of this topological space mod K. Okay, so it's important to know that each such C sub V is the underlying space or the polytope of a subcomplex of K. Each simplex of K being connected lies entirely in one and only one of these C sub V's. Okay, so you have this guy mod K, which consists of various components. Okay, each of them is so each of them is such CV. Okay, so this is CV prime, this is CV double prime, something like this. Okay, and each simplex of this complex K lies in a unique component, say C sub V. Okay, all right. So that was the first step where we show that C sub V is a component of mod K. Now we are ready to prove our theorem. Okay, so let's prove it. Step 2. Now let us prove the theorem. Let this collection V sub alpha be a collection of vertices containing one vertex from each component C alpha of mod K. Okay, so you have all these components of mod K and choose a vertex from each component and form such a collection. Okay, choose a vertex W of this complex K, then it definitely belongs to some component of K, right? Some component of mod K. So we arbitrarily choose a vertex from W, which we call W, from the complex K, and that then it belongs to one of the components of mod K, say C sub alpha. Okay. So in other words, from the definition of these C alphas, W, this vertex W, is equivalent to the vertex V sub alpha. Okay. All right. So C sub alpha is defined with respect to the vertex V sub alpha. Here we have denoted C alpha. We denoted the component C alpha with the vertex V alpha that is contained there. Okay. So W is equivalent to V sub alpha. Therefore, there is a sequence from the definition of this equivalence relation. There is a sequence A0 all the way up to AN of vertices of the complex K, of vertices of K leading from V alpha to W. So A0 is V alpha, and the last vertex AN is equal to W. Good. So now the one chain given by A0 to A1 plus A1 to A2 plus all the way up to AN minus 1 to AN. This is a one chain that is a linear combination of these elementary one chains, right? Okay. So this elementary one chain has value 1 on the simplex, on the one simplex A0, A1 to be 1 and elsewhere 0, right? And what is the boundary of this one chain? Has its boundary to be equal to AN minus A0. But AN is taken to be W and A0 is taken to be V alpha. Okay, so we have chosen a one chain whose boundary is given by W minus V alpha. Okay, so in other words, W minus V alpha is equal to the the boundary of this one chain, right? A0 to A1 plus A1 to A2, finally AN minus 1 to AN. So this is a one chain, and when we add delta 1, the operator delta 1 to that one chain, we get this W minus V alpha. So which means that W is equal to V alpha plus this boundary term, A0 to A1 plus all the way up to AN minus 1 to AN. Okay, so this is our equation number 2. So from this equation number 2, one finds that the zero chain W is homologous to the zero chain V alpha. Okay, so it's important to note here that we are engaged in abuse of notation again. Both the vertex and the zero chain and the elementary zero chain, to be more precise, corresponding to that vertex are denoted by the same symbol. Okay. Okay. So we does have seen that every elementary zero chain, so we have picked up this zero chain arbitrarily. Every elementary zero chain in the complex K is homologous to one of the zero chains in the collection, right? One of the zero chains V alphas appearing in the collection V alpha. Okay, hence any zero chain in K can be seen okay, because so we pick up the elementary zero chains of the complex K, and we have seen that these are homologous to one of the zero chains appearing in the collection. These are zero chains corresponding to the vertices V alphas. Okay, it's again the abuse of notation. They are written by the same symbol, the zero chain, the elementary zero chains, and the corresponding the vertices. Okay, so then if we pick up any zero chain from the complex K, that can be seen to be a linear combination of the elementary zero chains of the complex K. Okay, so that's why any zero chain in K can be seen to be homologous to a linear combination of the zero chains V alpha. That is, C is equal to N alpha V alpha, where N alpha are integers. Integral linear combination, of course. Okay, good. So now it's time to show that no non-trivial chain of the form, the one that we have just written, C is equal to N alpha V alpha, bounds. This is what we want to prove. Okay, so the zeroth boundary is going to be trivial, right? Proving that B0 of K is trivial. Suppose the contrary. Again, we proceed by contradiction. Suppose the contrary, that is, C is equal to delta 1 D for some one chain D of the complex K. So we have seen earlier in step 1 that each simplex of K lies entirely in one and exactly one component of K. So we have seen earlier that each simplex of K lies in a unique component of mod K. Therefore, each one simplex of K lies in a unique component of mod K. Now, using exactly the same arguments that one uses in the beginning of step 2 for zero chains, one finds that D is equal to sum over m sum of all these terms m alpha d alpha, okay, where m alpha, these m alphas are integers, okay, exactly similar argument. So we did that for zero chains. Now we are going to do it for one chains, okay, where these d alphas are elementary one chains, carried by the components C alphas of mod K. So remember that for the zero chain you had these V alphas, right? Instead of having D alphas, you had V alphas, which were the elementary zero chains corresponding to the vertices V alphas, each of which lies in uh, in a unique component C alpha of mod K, right? Good. Now I need room again. Now, since del 1D is equal to m alpha del 1 d alpha, right? So we are applying this operator del 1 to the one chain D, okay? And del 1 d alpha is carried by C alpha, is carried by C alpha, since d alpha is carried by the component C alpha, the its boundary. So the boundary operator acting on this d alpha is also carried by the same components, right? Okay, so that the integral multiple of the integral multiple of del 1 d alpha, that is m alpha del 1 d alpha, is also carried by C alpha. Okay, so we have arrived at the conclusion that each such term is carried by C alpha, and hence one concludes that this guy m alpha del 1 d alpha is carried by C alpha, and this is a zero chain, right? And so therefore uh, therefore this guy can be written down as n alpha v alpha for some alpha, and where n alpha belongs to the set of integers. Now the claim is that, okay, so because we are lying entirely in this component C alpha, it has to be n alpha v alpha. It's not a linear combination of zero chains that I was thinking, okay, because we are entirely constrained to lie in that component C alpha. It has to be an integral multiple of V alpha. Okay, there is no other option. So now the claim is that this n alpha, the integer, has to be 0. Okay, so this is what we need to prove. Let us take epsilon to be the map from the set of from the group of zero chains on the complex K to the additive group of integers. This group homomorphism defined by epsilon v is equal to 1 for each elementary zero chain v corresponding to the vertex of K denoted by the same symbol v. Okay, so this is how we define this map epsilon. So we pick up an elementary zero chain v corresponding to the vertex v and apply epsilon to it to get 1. Okay, so if you define this group homomorphism epsilon from the group of zero chains K to the additive group of integers in this way, then we see that epsilon of this delta 1, the boundary operator acting on this elementary 1 chain, VW, is going to be, this is nothing but W minus V, we know, and this is just 1 minus 1 is equal to 0 from the definition of this map epsilon for any elementary 1 chain V comma W. Okay, so one therefore has epsilon of m alpha d1 d alpha, okay, to be equal to epsilon. We have seen that they have to be equal to n alpha v alpha, right? And this is epsilon n alpha v alpha, and we know that epsilon of v alpha is equal to 1 for all alpha, so this is equal to n alpha. Okay, but since these d alphas are elementary one chains, one must have epsilon of delta 1 d alpha to be equal to 0. We have seen it earlier that epsilon of an elementary, epsilon of delta 1 acting on elementary 1 chain is equal to 0, right? So this guy has to be 0. And in particular, epsilon of m alpha del 1 d alpha has to be equal to 0, right? Which means that epsilon from here epsilon of n alpha v alpha is equal to 0, right? Since epsilon of v alpha is 1, one is forced to have n alpha to be equal to 0. Okay, for each alpha. So which implies m alpha del 1 d alpha is equal to 0. Why? Since because of this equality, m alpha d1 d alpha is equal to n alpha v alpha, right? And since n alpha is 0, this guy is 0. Okay, this is our equation number 3. Hence, we have arrived at the following. Del 1 d is equal to sum of all these terms, m alpha del 1 d alpha, which is sum of all these terms, right? Right, each of them is 0. So sum of all the zeros is 0. This is our equation number 4. So we therefore see that C is equal to del 1 d is equal to 0. That is a 0 chain that bounds is necessarily trivial. C is 0 is necessarily trivial. That is, the boundary, the 0 boundary of the complex K is trivial. Okay. Since C is equal to sum over all the alphas, n alpha v alpha, for a given 0 chain, a 0 chain is a cycle, and hence a 0 cycle. Okay, and there are no non-trivial 0 chain that we have just found. Non-trivial 0 chain that bounds this collection V alpha forms a basis for the zeroth homology group H0 of K. Okay, and this proves that this guy is a free abelian group because it has this basis, right? Free abelian. Okay, so we are done proving the first theorem. We take a break now, and then we'll discuss another version of the zeroth homology group using this augmentation map. Okay, thank you for attending the first segment of the second lecture.